At the end of section 5, we left off with cyclohexane and the fact that it's the most stable of the cycloalkanes. Right? And we saw this slide here. Right? Not only do we slightly twist out of a planar conformation to reduce the bond angle from 120 if it were fully planar down to 111, and close to where we want to be for 109.5, something that's sp3 hybridized. But all of our adjacent bonds are staggered, as we can see in the middle there with the Newman projection. And so there's no angle strain, so we have something that's exceptionally stable. Because it's exceptionally stable, it's super common. Okay, so we need to know how to draw the chair conformer of cyclohexane. And this is something that, were we taking a test during face-to-face lecture, I would always ask you to draw cyclohexane. So for right now, I'd put a star in this slide, 127. Make sure you know how to draw this in the future for take-home exams or when we are finally back to face-to-face. It starts by drawing two parallel lines, same length, angling slightly downward. Doesn't mention it in the text, but notice you start the second line at about the halfway point of the first line, and then you connect them with a V, or just three sets of parallel lines. So I don't usually do the V method. If you're trying to keep everything the same, I draw my two parallel lines, I draw these lines, and then I draw the lines on the side. Okay. So know how to draw the chair conformer of cyclohexane, and then know where the chair conformer name comes from. It's a silly little comic, just trying to illustrate what's going on. The four carbons in the middle are all on the same plane, but then the carbon on the right-hand side is pointing down, carbon on the left-hand side is pointing up. Okay, so it's just kind of a flip of what's shown here. Turn the guy around. Okay. Just envision it like a lounge chair, but you do need to know how to draw it, both getting the original structure and then how to fill in the bonds within. Okay. And there are two types of bonds to cyclohexane. There are axial bonds, okay, and those point straight up and down. Keeping in mind, I'm going to jump forward a slide and then come back, that when we draw cyclohexane like that, it's a side-on view. We're looking at the side of the molecule. So really, this is coming out towards us. That's going back. So then if we're thinking about it on the side, our axial, oh, sorry, I went forward. I meant to go backward. Our axial bonds here are pointing straight up and down. And then we also have equatorial bonds, okay, that are pointing at an angle. And a nice trick, with the equatorial bonds is they are parallel to whatever is two bonds away. So if you go one bond, two bonds, notice this line and this line are parallel. This equatorial bond, for example, go one bond, two bonds, it's parallel with that one. So your axial bonds, your equatorial bonds. Notice they also rotate pointing up and down. So axial, those are easy. You can see up, down, up, down, up, down. Equatorial, down, up, down, up, down, up. It's these two equatorial in the middle that tend to give people the most trouble. Okay? And those are pointing outward at a slant due to the bond angle. But if you can fill in the axial bonds, which are easy, you can just kind of follow the point, This looks like it's pointing up, so you point your axial bond straight up. If you can do that, then the equatorial bond that gets filled in is opposite. Axial points up, equatorial points down. Okay, we already discussed this slide. And cyclohexane can also interconvert between the two chairs. Okay, they are equally stable to one another. If you think about carbon 4, in this case being the feet of the chair, flip it around, it can become the head of the chair. When you do a ring flip like that, your equatorial bonds then switch and occupy the axial position, and the axial become equatorial. Okay? And that's just due to the ease of rotation, low energy barrier, It's super easy for that cyclohexane to flip back and forth, which is significant for reaction mechanisms later on in the class. There's also something known as the boat conformation of cyclohexane. If you take the foot part of the chair conformation and then flip it up. Okay. The boat conformation is actually also free of ankle strain. It has everybody reduced in that position, but it's less stable due to these eclipsed hydrogens right here. Right, they're called flagpole hydrogens. They point right at one another. Okay? So that's why the boat conformer, which comes, right, you see the name right there, less stable. Okay. The highest energy conformation is known as a half chair. That's if you were to flip the foot and kind of stop it halfway. Right? But just notice the key takeaway here, chair conformation, lowest energy. Okay. And it can, like we said, flip back and forth between those two chair conformations as long as all your substituents are the same. They have the same stability, right? And it's doing that, thousands of times per second. It's a rapid equilibrium at room temperature because there's sufficient kinetic energy to overcome the energy necessary to overcome this energy barrier right there. But I just mentioned that's assuming all the substituents are the same. It's just cyclohexane with hydrogens. Right? What if I put on a substituent, something that's monosubstituted? Then notice we're no longer equivalent in energy, okay? Because one conformation is going to have your substituent, a methyl group in this case, in the equatorial position, and the other one is going to have it in the axial position. Okay? And putting a substituent in the equatorial position is more stable because it has more space for that electron cloud that our substituent occupies, right? There's less steric strain. So notice our equilibrium has shifted, right? It's favoring the left-hand side here where I have my methyl group in the equatorial position. You can see that if you play with a model kit, right? You can also see it in the Newman projection right here, how that equatorial substituent has more room, right, than it does if I put it in an axial position. And that reduced stability in the axial position actually has a name. It's called 1,3 diaxial interactions. And again, if you build this with your model kit, you can see how one of those hydrogens from the methyl group, when it's in the axial position, is pointing straight at these other hydrogens. So that's called a 1,3 diaxial position or diaxial interaction, coming from these hydrogens coming in a 1 position and a 3 position. It doesn't have anything to do with the numbering for nomenclature of cyclohexane. Don't let that confuse you. It's just a general term, 1,3 diaxial interaction. And that's something that is really important to know. So you should be able to illustrate those diaxial interactions and know what they mean, why having a substituent in the axial position is less stable. And we see, right, if we have multiple substituents, again, right, we saw that looking at butane with a gauche interaction right there, it's less stable than anti. Axial is less stable than equatorial, kind of tying these concepts together. Know that idea, steric strain. Steric strain and angle strain are really big in the back half of chapter 3. And it should make sense if we're worried about that hydrogen on a methyl group pointing towards other hydrogens in 1,3 diaxial interactions, the larger our substituent becomes, right, the less it likes the axial position, okay? Less and less stable, it's higher and higher in energy. So that's the more we're going to favor our equatorial position, right? So look at this, as I go from a methyl group to an ethyl, to an isopropyl, to a tert-butyl, right? That giant group, look at the equilibrium change, right? 4,800-fold, it's going to favor the equatorial position over the axial position versus hydrogen, where it's 1-to-1. It's fine in both. So hopefully all that's making sense. We finished by looking at di-substituted cyclohexane, where we need to consider both substituents in the positions that they're in. So we're going to look at dimethyl cyclohexane, specifically 1,4-dimethyl cyclohexane. And I recommend you pause the video and try and draw that out. And when you're putting your methyl groups in on carbon 1 and carbon 4, you'll see that you have a choice. right? Where do I put them? And then is it cis or is it trans? Okay. And hopefully you recall that from Gen Chem. We briefly touched on it, but we're going to see it a lot in organic. Okay. You can have cis trans on opposite sides of a double bond. We've already covered that, right? And we'll talk about it again in chapter 4. But you can also have cis or trans isomers, which are called geometric isomers, on a cyclic structure. Okay? So keeping in mind, right, that we're looking at this cyclohexane from a side-on view. Okay? This methyl group points down, and this methyl group points down. So they're both below the ring. So that's the same side. This is cis 1,4-dimethyl cyclohexane. Versus over here, where this one points up, this one points down, those are on opposite sides of the ring. So that's trans 1,4-dimethyl cyclohexane. You got to be careful when you're looking at those in the cyclohexane chair structure, right? They've got to be either pointing the same way or opposite ways relative to the ring. And it's tricky, especially with those equatorial positions. And if you're wondering where the names come from, right, cis is for Latin, or they're both from Latin. Cis is Latin for on this side, trans Latin for across one another. So cis and trans. Cis is the same side, trans is opposite. Good. Excuse me. Each one of those isomers, the cis and the trans, can undergo a ring flip. But we have to pay attention to where the two substituents are going. And for our cis 1,4-dimethyl cyclohexane, one is going to have an equatorial and an axial position. And then remember, when I ring flip, everything that was axial becomes equatorial and vice versa. So then I end up with another one that's equatorial and axial. So in both situations, it's one equatorial, one axial. So that's an equilibrium. But down here, right on the left, for trans 1,4-dimethyl cyclohexane, I go from one structure where they're both equatorial, which remember is favorable due to steric strain, to another one where they both become axial, and that's less favorable. This equilibrium favors the left. So whenever it's possible, you want to put your substituents in the equatorial position. So the conformer with both of them in the equatorial position is more stable. And that could be cis or could be trans. It depends on the location of your substituents. So trans 1,4-dimethyl cyclohexane is more stable, but cis 1,3-dimethyl cyclohexane would be more stable, for example. And if you don't believe me, try drawing it out. They have to be cis to both occupy the equatorial position when it's 1,3-dimethyl cyclohexane. Okay. And we, in this situation, so I got thrown off by the order of the slides here. If you've got two substituents, you have diaxial interactions for both of them, so it's even less stable than what we talked about before. So it's almost double as unstable here. The larger the substituent, again, has a higher propensity to occupy the equatorial position. So if you're faced with that decision, put the larger group in the equatorial position. Okay? So if you look at all the structures on this slide, this one right here on the top right is the least stable because it has both groups in the axial position. Over here on the bottom left, right, we've done better because we moved the equatorial position, or sorry, the group, a large tert-butyl group, to an equatorial position, but I still have a methyl group in the axial position. Okay, so that's better than the alternative where I move the tert-butyl group back to an axial position. But what's the best possible combination? This one on the top left, right? Both equatorial. As long as it's possible, you put them both equatorial. If it's not possible, right, you're forced to have them trans down here on the bottom, then you're going to put your larger group in the equatorial position. Always put the bulkier substituent in the equatorial spot. Yeah, we finished with one quick consideration about two rings coming together. We actually see that a lot, especially in medicines. And when we have two fused rings, that means they share two adjacent carbons. So you can think about one whole ring as being a pair of substituents on the other ring. And if there's two substituents, they could be cis or they could be trans. Okay? But because they're directly next to one another, in this situation, trans is more stable when it's 1-2, okay? Because that puts both of them in the equatorial position. Okay? And so they end up looking like this. Transfused rings have both the substituents coming off in the equatorial position versus cisfused where they're less stable. Okay? So hopefully that makes sense. You see that, as I said, with medicines, hormones, steroids, a lot of things with the human body have fused rings like that. Okay? So the big takeaway from this video, cyclohexane is huge, right? We just talked about it effectively this whole section. So 3.13 through 16 here. So know how to draw it, cyclohexane, know how to draw the chair conformation, know how to draw the axial and the equatorial bonds, and know where to put the substituents. If it's just one, you're always going to put it in the equatorial position, right? But if you have two, then we've got to play a game. If we're allowed to put them wherever we want, we're going to put them both in the equatorial position. But if we're told it has to be cis or it has to be trans, you might run into a situation where one of them has to be axial and the other equatorial. In that case, put the larger group in the equatorial position.